Good evening, good morning, everyone. I'm Antoinette Young, and I'll kick this off for us. If Prasang, if you can go to the next slide. So this was a project that Prasang and I did under Anand's guidance. Slide. And we're going to discuss some of the research that we did as a result of a pain point that we were hearing from a couple of our clients. We'll jump into our solution and the approach that we use to solve this problem based on several requirements. This research, sorry?
Can you show your video?
Sorry, I can't hear you.
Can you enable your video?
Let me try. Okay.
Okay, thank you.
1 second. All right. Okay, so we'll jump into our solution and approach that we use, to solve this problem based on several requirements that we had. So this research was geared towards how do we help our clients that were experiencing supply chain issues, especially when it relates to shipping. So shipping is an essential part of every supply chain that can be used with a combination of road, sea, or air. And as cargoes moves from its origin to its destination, it's exposed to various environmental factors. And there could be the possibility that damage can occur no matter what mode of transportation is being used. So cargo loss is a global problem. And according to the National Cargo Security Council, studies show that the financial impact is around 50 billion each year worldwide. Can we slide? So ensuring the cargo makes it from point A to point B safely and intact is one of the most important objectives for supply chain. But still, almost 76% of companies have reported having at least one supply chain disruption in the past 12 months. And for those companies that use less than a truckload, also known as LTL, where they move cargo, they're at a greater, or they're exposed to greater risk than full truckload shipments. So as LTL cargo is moved through complex networks, it's not uncommon for this type of cargo to be loaded and unloaded 4 to 6 times before it actually reaches its destination. Each step increases the risk of breakage, theft, or items being lost. So the same would also apply for international full container shipping routes. We can slide. All right, so when there are tight profit margins, a single damage shipment can have big financial impacts, especially on small to medium-sized companies. It could be a 15-to-1 ratio in the amount that product needs to be sold to offset what was lost or write off the damage or lost cargo. So as an example, let's say a company has a net profit of, let's say 7%. If that company lost a shipment worth 100,000, it would take an additional 1.5 million in sales to pay for that lost shipment. So the potential risk for such large losses pushes many shippers to insure their cargo, but an increasing number of claims causes insurance costs to rise, and insurance policies are largely denied at a rate of 50% of overall claims. We can slide, Prasang. All right, so the impact of goods getting damaged while in transit goes well beyond the cost of replacement. There could be damage in relationship with customers, especially if the damaged goods cannot be replenished in a timely manner. So some other factors could include interruptions to supply chain, higher insurance claims or premiums, loss of productivity due to filling out claims, tracking down return orders, repackaging and shipping are just some of the things that add to the financial cost of damaged shipment. So whether it's due to poor packaging, water damage, or other outside forces, cargo damage is a reality that most companies will have to deal with as their goods are making its way to their customers. So to prevent cargo damage, we need to actually understand the environmental conditions and what type of damage the cargo may endure while it's on its journey. This gives the opportunity to optimize the packaging and mitigate cargo damage as it's being shipped from point A to point B. So I'm gonna turn it over to Prasang to discuss our approach and solution to helping prevent cargo damage.
Thanks, Antoinette. And as Antoinette has covered the impact of the problem, both which the organizations face directly as well as indirectly. So having an understanding of the issue that it revolves around it, let us discuss the techniques to mitigate these issues. So a survey was conducted by the Global Supply Chain Institute at the University of Tennessee in 2014. The goal of the survey was to find out the preference of firms with a supply chain arm towards risk mitigation of cargo loss and damage. So the results they obtained were quite interesting in our opinion. The graph in the center actually shows the results, and it shows the preference of different organizations towards risk mitigation techniques on a scale of 1 to 10, with 10 being the most preferred. So we'll go over and discuss each of these techniques. The most preferred technique one on the extreme left is the strong suppliers. This involves having financially strong, competent world-class suppliers with ample experience and proven track records. However, it takes approximately 2 years to develop and fully certify a global supplier, so it's an issue. The second rank strategy that is mentioned is compressed cycle time, and this is again this one reduces the time required to produce and deliver a product, and in order to actually increase the throughput and become more flexible and responsive to customers. So this one is achieved by mapping the value stream of the end-to-end global shipping process, and looks for ways to reduce waste and eliminate delays at every step. The third rank strategy that we have highlighted is the visibility. And this involves using visibility tools to actually increase the visibility of the end user in the in tracking the global shipments and take action whenever necessary. And this is possible by using supply chain event management to send alerts to key personnel when action needs to be taken by someone somewhere in the global supply chain to address potential issues or delays. The next one is global logistics competency, which is very similar to the strong suppliers, as it leads to selecting competent logistics partners to manage the shipping process. The next one is actually, in our opinion, arguably the most sophisticated among the list, and that is to predict, given historical data, the possible damage sources in a supply chain. And this would take in historical data, and this would include some kind of a model that takes in historical data and some other demographic features. And it has the same preference value as arguably the least sophisticated amongst the methods, and that is just using air freight or expedited shipping wherever possible. The next method is using additional inventory, or that just deals with having an additional inventory whenever or wherever a cargo damage is occurred, so that there's no pressure on the inventory. And since this method is more kind of reactive and doesn't really help dealing with the problem of cargo damage, it is not a highly preferred one. Another method with same preference as this one is near sourcing, and that involves setting up supply chains in nearer geographical locations and not consider long journeys of cargo to be traveled. Then this one is again runs into several problems because as several things are being set up, there are a multitude of changes that come with changing the supplies, etc. The last two methods are reserve funds and purchase insurance, and these are mostly monetary ways of mitigating the risk. So one method deals with reserving the fund for any unforeseen or unexpected disruption, and the second option involves claiming the said amount after the event has taken place. So in a nutshell, most of the techniques that are most preferred involve either accelerating the shipment in one way or another. So techniques like compressed cycle time, logistics competencies, strong supplies, and even air freight or expedited shipping all ensure the same stuff. Predictive modeling deals with the problem in another way, as it models the historical data and predicts whether what is the probability of our cargo getting damaged in a particular route. However, we'll be focusing on the visibility section of the process in this study, as other methods that may be employed use business frameworks and high-level risk analysis, and this lays out even operational guidance for the cargo. However, these run into major problems due to language spoiler due to cross-country transfers. So as we mentioned in this study, we are majorly focusing on the visibility technique, which was pretty high ranked amongst the other techniques in terms of preference. However, the visibility technique can mean two things. One definition could be a basic location tracking, just increasing the visibility of the cargo shipment based on where it is at any point of time. It can also be interpreted as a more involved impact tracking with the location information. So the former problem can be easily solved using a GPS sensor, but since we are targeting to generate as much insight as possible into the supply chain, we will discuss the latter one, that is in using the impact tracking with the location. So it is not surprising that there is already a solution in place for using this method, and that is just using straightforward impact and force sensors for tracking shipments along the route. And this goes well with the along with the basic GPS and all that jazz. However, as we mentioned that this solution is already present, there are several shortcomings that comes with it as well. So what we are planning to do is trying to overcome some of these shortcomings with our proposed solution. So the first problem that comes is the problem of cost. The impact sensors that we mentioned are very costly, and a typical impact sensor ranges from about $1,000 to $6,000 based on the specifications selected. The huge cost associated with these make them viable for use as trackers for only very expensive cargo, which constitutes just a small fraction of the large amount of cargo being shipped every day. So what we propose of using is using cost-effective accelerometer sensors, which cost about $1 each. This way they can be used even for very cheap shipments. The second problem that arises is the battery life. These sophisticated devices that we mentioned consume more power, and we found a typical sensor to be rated for around 64 hours for trigger-based low-power acceleration trigger using assuming say 99% sleep mode duration. However, what we found out was in case of continuous monitoring, these have to be recharged or attached with a battery, which would make the whole package cumbersome. On the other hand, we explored an accelerometer sensor, and with similar tracking numbers and similar trigger performances and an optimized cloud flush frequency, we got a battery life about 100 days with the same sensor, which is more than enough for any kind of shipment. The third problem is the extra logistical effort that is involved. So this is not easily quantifiable as the other two due to several dependencies, but it is a major issue nevertheless. Since the sensors, impact sensors are very costly, there is a need to recover these to be reused again for another shipment. However, this comes off as a separate logistical challenge with an added shipment requiring affecting the overall shipment cost as well as man hours to track and manage the same. Due to the low cost of the accelerometer sensor that we used, there is actually no need to recover them, and they can be just disposed of after every shipment, again saving cost and overheads. Having discussed how we are planning to overcome some of these shortcomings, let's discuss our solution. So we present a solution which has three main focal points. One is it needs to be cost effective. This would ensure that our solution is viable for a variety of cargo, both cheap and costly. Secondly, it should be easy to set up, and it should have the ability to integrate into current supply chain processes that are already laid out by the firms. So we understand that changing already laid out processes is very difficult in a real life scenario, and thus our aim was to come up with something that can be implemented with very little changes required to the current processes. And thirdly, it should meet the needs of different cargo and shipping methods, so as to maintain viability for all, and this allows a solution to be as general as possible. Since we have discussed the focal points of our solution, let's discuss a problem that was faced by one of our clients, which Antoinette highlighted. So our client was a large exercise equipment manufacturer, and they had a problem of their equipment getting damaged while it was in transit from its factory to the retail outlets. So this damage resulting in sizable losses for the company. The goal of the project was to increase the visibility of the client in the shipment process of the equipment from the factory location, which was present in the somewhere in the East Asia to the US. In addition to that, we also had to provide insights which would support them to find out where exactly or where the most probably their equipment is getting damaged through the whole shipping route. So this was required to take any corrective actions that they might take in the right places to improve the robustness of their whole shipping process. So having received the details of the shipment route from the client, so it listed the requirements for the device that needs to be used for tracking the impacts. So, I mean, these requirements are valid even for the general problem of cross-country shipments as well, as our client problem is not very specific and is more or less general in terms. So firstly, the device should be able to connect to the cloud and send data while roaming. Now, a good strong point to note over here is that since there is no Wi-Fi, BLE, or any other sustained network that is guaranteed throughout the shipping process, it should be able to do this using cellular networks due to its large coverage. So for our particular case, we decided to go ahead with 3G with a 2G fallback. At the time the project was was done, the 4G was still limited. We decided to go for 3G for connection speeds. Also, since 3G was not widespread, we decided to go for a 2G fallback in case there were no 3G signals available. The connectivity options, secondly, the connectivity option should also be nation agnostic due to cross-country shipments. This again was solved by the cellular technology, as there are a lot of suppliers offering global cellular options. Thirdly, as already discussed, the device needs to last the entire journey without the need to be recharged. So this includes, I mean, if there are any recharging options, this includes laying out operational guidance and also ensuring if there is a battery present, then it must be ensured that the tracking device needs to be waterproof, and overall it should maintain a conducive environment for the externally attached battery, which again is a strong overhead and leads into several logistical issues. Lastly, it should have sufficient onboard memory to record and store events before a data flush, because if there isn't, then based on the frequency of the cloud data flush, it may lead to a loss of precious data. Coming on to what exactly we did, we selected an accelerometer sensor that was housed in a multi-purpose device. And that also, this device also contained other basic sensors like the temperature sensor, humidity sensor, GPS, etc. And we ensure that the device we select can sustain rough situation, both in terms of the environmental factors that it faces, as well as the it should be rough enough to handle the rough handling by the handlers. On the software side, we modified the firmware onboarded to ensure that the requirements we discussed in the previous section are all covered. So firstly, there was a need to convert the accelerometer raw values to impact values, which made physical sense. Now, since in the case of impact sensors, they directly return the value of impacts, since they are exactly what they call it, impact sensors. But since we are using accelerometer sensors, we used to get values, scaled values from -512 to 512 for each axis. And hence these values don't really mean anything as of out of the box. So we carried out some calibration experiments to map this range onto an impact value range in G-force, and that is represented by the symbol V over here. And we calibrated and got the value of the lambda that we mentioned. So the next task was to calculate two thresholds. So one threshold was more in line to save battery. So we called it Vmin. That's present in the second equation that we showed. So we configured the accelerometer to record and report values only if the impact experienced crosses this particular threshold, and this particular threshold was set at such a rate that it should have any value be below this. It shouldn't have any, it can be just negated, as this impact value was just too small to be of any consequence to the cargo. So this in turn helped us to extend the battery life to ensure that the device lasted for the whole shipping route without the need to be recharged. Other threshold that we have mentioned over here, that we have mentioned by Vmax, this what we call it the breakage point. This breakage point would be the impact value faced by the cargo, after which beyond this value, it will it is highly likely that it is going to face some kind of damage. So this threshold value is calculated based off of consultations with the client, subject matter experts, and also considering the type of cargo and the ship and the packaging that they were using. So any impact value above this threshold it carries a high chance of damaging the cargo. Also, apart from setting up the impact values and the thresholds, we for extending the battery life, we optimize the cloud connection and data flush frequency. So there are two opposing trade-offs that run over here. So if the data flush frequency is very frequent, it would drain out the battery much faster, as connecting to the cloud is a battery intensive task. However, on the other hand, if the data flush frequency is very less, then it would put more pressure on the device's memory, and there are chances that the memory caps off before the next data flush, and hence it will lead to overwriting of data and loss of data. So this would hamper the near real-time performance of the data set. Hence, a sweet spot was found based off of these considerations by tuning this. Having all the components tweaked, this is the whole solution architecture with major components highlighted. The first layer is the hardware layer. These consisted of the devices attached to the cargo being tracked. This layer would record the impacts, store them, and then periodically send them over to the cloud. The next layer was the data layer, which majorly held the cloud, and this would the major role of this layer was to hold the data that has been sent by the devices, sorted with their device IDs, etc. Also, preferably, an API can be hosted on top of this database to manage any data pull requests to maintain sanity throughout the project. The third layer, highlighted in blue, is the data ingestion engine or the compute layer. So this was built on an application enablement platform, and this consisted of webhooks to and API calls to fetch the data, and it also included general device management, which included keys, etc., to access the data for specific devices. And this layer also performed the computations that we highlighted in the previous slides. The last layer was a presentation layer, which constituted a dashboard with all the insights computed by the ingestion engine, published to the ingested user by the end user. So this is what the dashboard looked like with all the insights available for the user. So apart from the general options like to switch to a particular device or log in or log out, the impact plot was present on the top. And this shows the impacts faced by the selected device over shipment time. It was also color coded, signifying different regions in the shipment journey. For example, these red lines constitute the devices when constitute the impact faced by the device when it was at the port in East Asia. These blue impacts were experienced by the device when it was being shipped by sea in a container, and these green impacts were faced by the device when it was actually being transferred from the port in the US to the factory outlets and the inventories. It also had a horizontal demarcation line that was calibrated, and this divided the impacts into low impact zone and high impact zones. So for example, we can see over here that most of these red lines and the green lines are crossing the threshold of our high impact region, and all these blue lines are well below the threshold. So this signifies that it is more likely that our cargo is getting damaged either in the ports in East Asia or in the road transfer from the ports to the US, and it is very less likely that the cargo is getting damaged in the sea route. In addition to the impact plot and all the insights that came with it, we also provided other stats, as well as we provided the last known device location and the last known battery and the temperature of the device. So all of this was aimed at providing greater visibility to the whole shipment process to the to the client at the end. So methods like better packaging or better transporter selection for different routes could be undertaken. Also, every method that we discussed can be replicated for other problems as well as this problem, as we discussed, is a general problem. The only thing that needs to be changed is the threshold calibrations based on the cargo, the shipping route, the packaging, and the specific requirements of the RLD. So that's it from my side. Thanks for paying attention. The questions?